Okay, so today we'll again have some tutorials problems, which is about the line integral we just learned 2 days ago. Okay, so I'll give you some time. Okay, again, these tutorial problems can be found on Blackboard, but before that, okay, so let me again say a few words about how do we make parameterization, okay, for a path that we are going to do line integral with, right? So remember that last time we are considering a coordinate system with vector fields, right? So we start at some point and then we end at another point, right? So let's say this is x naught, y naught, and the second point is x1, y1, right? And then we pick a path, right, to connect these two points, and then we do the line integral, right? The line integral that we are considering is this. And we have a procedure which is known as the parameterization, right? So which help us to convert the integral in t, right? Some parameter t. Okay, so basically you could imagine that t could be think of as time, but it doesn't have to be. It's just a mathematical parameter, right? So then what we need, right, is that we need to express this r as a function of t, right? And this r is a vector that goes from this, right, initially, and then finally go to the endpoint. So at some time t, right, the tip of that r has to be somewhere in between the two the 2 points, right? So let's start with the simplest case where I have straight lines. I have a straight line connecting the two points. Okay, so I'm just going with the simple case that I have straight line from here. So I just make a straight line. Okay, not very straight, but this is a straight line that I'm going to consider as my path. Okay, so then how do we do the parameterization? So we know that this r as a function of t can be written as some x function x hat plus y function y hat, right? So x represent the coordinate, x coordinate of that particle, right? So at t, and then this y is the y coordinate of that particle at t. So to make the parameterization, right? So first of all, the first step I would do is that I want to find out the equation for this line. Okay, the equation for this line. So the equation for this line is, okay, very simple. So it's just y minus y naught, right? X minus x naught equals, well, the slope, right? So you know that the slope is just y1 minus y naught divided by x1 minus x naught, right? Which I call m. So that means this equation is y equals mx minus x1 plus y naught, right? So this is the equation for this straight line. So then if we do the parameterization, okay, one simple way is that I simply set x as a function of t is given by t. Okay, and we know that t has to go from the initial point x naught, and then it's end at the end point x1. So from t equals x naught to t equals x1, right? So again, if you really think of t as time, then you will find it strange why I say that time is some position. But again, as I said, t is just a mathematical parameter. It does not have to mean time necessarily. So then my y as a function of t is given by this, right? mx minus x1 plus y naught. And this x is given by t. So that's why my y is t minus x1 plus y naught, right? So then you have this parameterization. Then next you can find this drdt, right? And then you can substitute back to your integral, and the whole integral now is expressed in terms of t, right? And this is the lower limit of your integral, and this is the upper limit of your integral. So then, of course, this is the simplest case where we have a strict path, right? So, but even I have other paths, right? I can still do it without too much difficulties. So as long as the path is not too complicated, right? So let's say if I have this time again, I go from this point and this point, and suppose both of this point is on this parabola y equal x squared. Okay, so suppose I start at this point on the parabola, and then I end at this point, the other point of the parabola, right? So again, x0 is my initial coordinate, x coordinate, and x1 is my final x coordinate. So again, I need parameterization. So I need this vector r as a function of t, right, to be like this. Right, initially this r has to be pointing here, and then after some time it has to be pointing here, and then some time is here, and then finally it has to be there. Okay. Again, the tip of my r vector has to be going along this parabola. So again, I can just set this x just as t. Okay, and again, I need t goes from x0 to t go to until t reach x1. So then y is x squared and x is t. So that's why this is t squared. Okay. So in the tutorial problem, you'll see that the first problem you do is an integration over a straight line, and the second is over a parabola, and then the third one will be over a semicircle. Okay, so so let me draw a full circle like this. Right, so this is, let's say this is x squared plus y squared plus I'm sorry, equals r squared. Okay, so now let's say I want to go from here to here, right, along the upper half of the circle, right? So then parameterization, right? So if you just use the same idea here, right? So you would think that, okay, what about I pick again x to be t, right, and then y to be this, right? So can you do that, right? So right, from t equals this is at r, right? This is at minus r. From t equals r to t equals minus r. So following the same idea from the last case, right? So this is something that you can do totally all right, right? So but what you probably find is that it will be more convenient to do the parameterization like this, right? Okay, so this is usually how we do it. We take care of a circle. Okay. So now you can just start doing the problem. Okay, so I don't want to spend too much time on it because we still have a lot of contents to go through. But so try the first 3 problems, okay, but just convert the integral to an integral in t and stop there. Okay, just don't bother to find the final answer. Just make sure that you are able to convert this, you're able to express this line integral, okay, in terms of an integral over t. So again, you can find this file on Blackboard, okay? Okay, so for the first one, right? So integration line integral over a straight line, right? So it'd be helpful that you first draw a picture. Okay. So we start at the point 3, 7, right? And then we end at this point 0, 12. Okay. So first step, as I said, you may want to find the equation of the line, right? So what you should be able to find is this one. Right, so this is the equation for this line here. Okay. So then parameterization, right? So R as a function of t is x of t, x hat plus y of t, y hat. So again, I just simply put x as a function of t to be t, and then y to be minus 3 divided by 3x, right? That means it's minus 3 divided by 3t plus 12. Okay, so t goes from 3. So initial x coordinate is 3. So the final x coordinate is 0. So it's okay to go negative. Right, so from t equals 3 to t equals 0. Right. So next we need to find this, right, dr dt. Right, so which is just dx dt x hat plus dy dt y hat. Right, so then I just have this x hat minus 3 divided by 3 y hat, right? So now the line integral so it's converted to an integral over t, right? And t goes from 3 to 0. So what you need to do is a dot product, right, between this f and this dr dt. Okay, so this dr dt is something that we found already, and f is this one, right? So, and of course, f is a function of x and y, but you need to express that also as a function of t, right? So then I have for f, the x component is y squared. Y squared, that means this whole thing square. So minus this 3x minus 6y, right? So 3x means 3t. And this minus 6y is minus 6 times this whole thing, right? So this whole thing is my field F. And then my dr dt, right? So it's just x hat minus 3 divided by 3, 5 divided by 3 y hat, right, dt. So then you just do the dot product, right? So x component of this multiplied by the x component of this. So it's just this term times 1. Okay. So then y component times this y component. And it's just plus 5 divided by 3. And if I simplify it a little bit for this, then I'll just get 13t minus 72 dt. Okay. So this is where I would just stop. Okay, so you now it's just an integral over t, then know how to do it. So then the second question, right? The second question is a parabola. It's a parabola shifted down by shifted it's a shifted parabola, right? So like a parabola like this. No, I'm wrong. Shifted the other way, the other side. Should be like this, right? This is 1. Okay. So we start at this point, where x equals 0. We end this point, x equals 3. So we are moving along this path. Okay. So again, it's the same thing, right? So parameterization. So x, just set it to t. T go from 0 to 3. So this time the y of t is t minus 1 squared, right? So then my dr dt would be x hat plus t minus 1 y hat. So in principle, can I set x equals 2t in terms of t? Right, you can do that if you want, right? So I do that, then I just have a 2 here, but then my my limit will go from 0, right, to 3 divided by 2. You actually make that choice. And also this y as a function of t is 2t minus 1. Okay. So now the line integral from 0 to 3. And then again, my field is here. Need to convert all that to t, right? So y square, that means it's t minus 1 square. So it's t minus 1 to the power 4. And then x square minus 4, right? So then it's just t square minus 4. Okay, so this is my field F. So dot product with this dr dt, x hat plus t minus 1 y hat dt. Okay, I'm not going to repeat the same process again, right? So you know how to take this dot product, and you have this integral as a function of t. So this one, integration over a semicircle, right? The upper half of a circle centered at the origin. So like this, and it has a radius 1, right? So that means I go from here, x equals 1 to x equals minus 1. So I'm doing counterclockwise rotation. Okay. So as I said, when we have circle, then we write down this. So because the radius is 1, so just 1 times cosine t and then 1 times sine t. Right, so that's it. So then if you want to find again the dr dt, so that means it's the d cosine dt x hat, so which is the minus sine t x hat, right, plus cosine t y hat. Okay. So now my line integrals becomes, okay, so okay, I forgot the limit. Okay, so what about the limit? So I go from here all the way to here. Well, when I'm here, so t is 0. When I'm here, t is pi. Right. So, or you can always say that, okay, from t equals 2 pi to t equals 3 pi. That's also work. Doesn't matter. So from 0 to pi, and then now the field f, right? So now I have this 3 times sine t x hat plus x squared minus y, right? So cosine square t minus sine t. So this is my field f, right? So, and then dot product with this minus sine of t x hat plus cosine t y hat. So after doing all the dot products, you'll find something like this: 3 sine square t plus cosine cube t minus sine t cosine t dt. Okay, so to do that, you just need to use some trigonometric identity for some of them, right? So for the first one, you can write it as this, right? So this is just something that you memorize, the trigonometric identities. And the second one, I could do cosine cube t is cosine t times 1 minus sine square t. And then the last one is just 1/2 of sine 2t. So then this is, I believe this is something you can do easily. So these are the first 3 problems for this tutorial. And there's a 4th one, but we are not there yet. Okay, I need to move on to the lecture notes. And then if we have time later today, we'll finish the 4th one. Okay. Okay, so what do we have last time? So we are considering, of course, line integrals, and especially towards the end, we are also talking about line integrals around a closed loop. Just like here, around a closed circular loop, let's say. So, and I was saying that, okay, you find that for some cases, after doing this closed loop line integral, you get 0 result, and for some other, you get non-zero result. Okay. So later today, I will get back to this point. Okay. And then now, what I want to consider is that I'm going to shrink down the size of this loop. Okay. So again, I have this vector field. Okay, this is a more complicated vector field, but I'm considering a very small loop. Okay, so this time I'm using a square loop instead of a circular loop. Okay, a square loop. It is very, very small. It's very, very small that this length, horizontal length here is delta x or dx if you like. And then the vertical one is this delta y, dy if you like. So now what I want to do is the line integral around this tiny closed loop. Okay. So basically, right, so the each side, right, has a very small length. Right, so if I do line integral, okay, but if I do line integral, so I basically need to take care of 4 tiny segments only, right? So when I do this line integral, so all I need to do is that, so suppose this one, I say this is my dr1, this part, and then this is my dr2, say this is my dr, okay, no, actually I want this to be 1, okay, this to be 2, this one to be dr3, this is 4. I should use another color, but okay. So that means if I do this line integral, basically it's a sum of 4 terms, right? Is f dot dr for this dr1, right? So I'll just call f1 dot dr1 plus f2 dot dr2 plus this side is f3 dot dr3, and then last f4 dot dr4. So really, this line integral is become just a sum, but because its loop is so small, so it's a sum or the contribution of these 4 tiny line segments. Okay, so now you'll say, okay, when I move along this dr1, okay, so when I move along this dr1, so what is f1? So the f1 that I'm going to take is just the value of the field at the midpoint of my side 1. Okay, when I say f1, so I'm taking the f value at this midpoint here. Okay, and then similarly, when I say f2 dr2, then I'm taking the f at the midpoint of my dr2, and so on. Okay, so then with that, I'm going to write this line integral as a sum of 4 terms, as I said, right? So this is side 1. Okay, be careful for each term. Okay, this is side 1. Okay, so the f value at this point, what is it? So I forgot to mention that at the center of the square loop, I say the coordinate to be x and y. Okay. So I want to take the f value at this point. So that means, what is the coordinate of this point? The coordinate of this point is x. It's also x, but it's a bit lower than this point. It's x, but the y coordinate is y minus delta y divided by 2. Okay, so this is, let me try to, so this coordinate is x, y minus delta y divided by 2. Okay. So this is how I take care of the first side, side 1. Side 1, I'm going along the horizontal direction, so that's why my direction is x hat, and my length is, of course, is delta x, so that's why my dr1 is x hat delta x. So now side 2, I need to consider this point over here. Okay, this point, the coordinate is x plus delta x divided by 2y. Okay. And when I'm walking along this vertical line, my dr2, of course, is in the y hat direction, right, with the length delta y. So that's why this is my side 2. This is my side 2. So same procedure, right? When I take care of this side 3, so then I need to take the f at this point. Okay, so what is this point? So this point, of course, is x y plus delta y divided by 2. Right. And when I'm walking alongside 3, I'm going in the negative x direction. So that's why my dr3 is minus x hat times delta x. So same thing for this 4. Now I have this 4. So now this line integral over this tiny loop is written as a sum of these 4 terms. Sum of these 4 terms. So next, okay, that's the important step. What I have over here is exactly the same as what I showed you in the last slide. Okay, so what I have over here. So then the next step is that from here to here, I'm just regrouping terms. Okay, no other tricks are involved. I'm just regrouping terms. Okay, so what you can see is that I'm regrouping the second and the 4th term over here. And then I'm grouping the 1st and the 3rd term over here. And then you can see that I divide this by delta x, and then I multiply by delta x. And here I divide by delta y and multiply by delta y. Okay. So now, if you just look at this term, this is exactly telling you the change of this function, the change of this function over a small distance delta x. So this is a derivative now. This is a derivative. So, and you can see that I'm considering x plus delta x divided by 2 and x minus delta x divided by 2, but I'm fixing y. So then this is a partial derivative, the partial derivative for this n function. Partial derivative with respect to x for this n function. Okay, I think I forgot to mention m and n. Okay, the field is written as this mx plus ny. Okay. So now this is the meaning, right? The first term is actually a partial derivative for n with respect to x. And then similarly, if you look at this fraction here, again, this time I'm considering the change, right, in the y direction. I'm fixing x. So this is the partial derivative of capital M with respect to y. Okay. So now I have 2 partial derivatives. So again, right, so as we take the limit by delta x, delta y tends to 0. So then basically just delta x becomes dx, delta y becomes dy. And that this term minus this term, right, becomes what we have over here. That's what I just said. Partial n, partial x minus partial m, partial y. And multiplied by this tiny element here, right? So this delta x, delta y, which I call dA, you understand why I call it dA, right? Because it is exactly the area enclosed by this loop. Okay. So now this line integral, okay, suddenly becomes this some partial derivatives. Okay, so multiplied by the area enclosed by this. And this term is very important. This one is called the circulation density of the vector field. Circulation density of the vector field. Okay. It will be clear later why it's called circulation. Okay. So circulation density of the vector field. So here is, I have an example function. Okay. So this is a vector field. Okay, it's a very long expression here, but if you plot it, what you'll find is something like this. So we have kind of 2 vortexes, right? So one here is kind of going anti-clockwise, right? The other going clockwise. Okay. So basically, it's a superposition, basically a superposition of 2 vortexes you could think of. Okay. So and now this is my vector field, and if I want to, so for each point, for each tiny region, I could calculate the so-called circulation density, right, using my formula over here. And if I do that, this is what you will see. Okay. So what you will see is that if you are kind of away from either of the vortex, like if you are here or over here, so the curl of F, right? So the circulation density, the curl of F is very small, almost zero. Okay. So that's the region where you can see that the field are kind of uniform, going in one direction. So they are not rotating, like they are not circulating. So that's why over here you see that the curl of F is zero. And however, if you are considering the region, right, close to the vortex, then you are getting significant numbers, values for this curl of F. Okay. And you can see that for this vortex on the left, I get positive value for curl of F, and then for the other one, for the other vortex, the right, I got negative. Okay, and it indicates whether it's go anti-clockwise or clockwise. Okay, so when you have anti-clockwise circulation, then you get positive value of curl of F, and if you get negative value of curl of F, then that means you are having a field that's going clockwise. Okay. So this examples give you some sense on why this curl of F called circulation density. Okay. Okay, so now I have considered this very, very small loop, right? But now I want to take one step backward. I want to go back to some regular sized loop, okay, some big loop. And then we'll see how this result for small loop could help us there. So what I'm going to consider is a rectangular loop like this. And suppose I do a line integral. So this is a regular size, a big rectangle. Okay, you could imagine there's a big rectangle loop. So I call this C, and then the area enclosed by this C is A. So what I'm going to do next is that I'm going to divide this region in half. Okay, let's say 2 equal halves. And then now for this boundary, I add lines here. So now I basically split this one big loop into 2 smaller loops. Okay, this C1 and this C2. So now I'm going to ask the question is that so if I do the line integral around this big loop C, I get some numbers, right? So now if I do the line integrals around this smaller loop C1, take the result and add with the value of line integral around the other loop. So that means this one plus this one. So I'm going to argue that the value of the line integral over the entire big loop is the same as the sum of these 2 smaller line integrals. Okay, and the reason is simple, is because when you consider C1, right? So when you consider C1, so you need to take care of how many segments, right? Again, 4 segments. So 1, 2, 3, 4. Need to do integration 4 times. So if you consider the other loop doing the line integral, I'm also going to have to do it 4 times. I call this 5, 6, 7, 8. So that means I have 8 segments to take care of when I do line integral. However, I have 8 terms, but look at term 2 and term 8. When I do term 2, I'm going from here all the way up here. So I'm walking to the upside. Okay. So when I'm doing, on the other hand, when I'm doing number 8, right? When I'm doing number 8, I am actually walking like this downside. Okay. So, but I'm walking at the exact same line, right? So that means that the field that I experience over that line will be exactly the same. But since I'm walking the other direction, then my dot product has to add a minus sign. Right? So, and that means the line integral over segment 2 will exactly cancel the line integral over segment 8. So that means at the end, I only need to take care of 1, 5, 6, 7, 3, and 4, by 6 of the parts. And these 6 parts, right, exactly give me these 6 parts. So because of the cancellation for the middle line, so the line integral around this big loop is the same as the sum of the line integrals for the 2 smaller loops. So now I'm going to repeat the same procedures over and over again. 1 split into 2, 2 split into 4, and so on until I have so many loops that each of them is just a small square loop with length and width dx dy, right? So now it comes back to the situation where we have just discussed a minute ago, when we want to talk about the line integrals around such a tiny loop. So, and note that I'm considering a rectangular loop, right? So then it's natural to think that you can divide it into these small squares. But okay, even though if my loop, the loop that I start with, is an irregular shaped loop. Okay, as long as you could imagine, as long as all the squares are small enough, right, they can all still fill up this arbitrary shaped region. So it's okay. It doesn't have to be starting with this rectangle. So the bottom line is that give me any loop of arbitrary shape, right? I can always divide that and then give you many small loops, okay, with each loop of length dx with dy. Okay. So we know how to calculate the line integrals for each small loop, right? It's just taking the circulation density times the area of this small loop. So then that means now the argument is that the integration, line integration over the entire loop, big loop, is the same as the line integrals, right, over every loop, right, in this region. So this one equals to a sum of each tiny little loop integral. Okay. And when I look at this one, it can be converted to a double integral, okay, over the region enclosed by the loop. So this double integral over a region is something that we learned in the last chapter, right? So now you'll see that suddenly we were doing line integral, so now it is suddenly converted to a double integral over a region enclosed by the loop. Okay. So this is known as the Green's theorem. Okay, and I have this bracket circulation curl form, or it's known as the tangential form, okay, because there is another form which we'll talk about later, known as the normal form. Okay. So this tells us that, right, this line integral can be equals to the double integral of this curl of f over the region enclosed by this loop C. So and remember, okay, when we take this line integral, okay, over this loop, I always do it counterclockwise. So if you do this closed loop line integral in clockwise, then you need to add a minus sign for the right hand side, of course. Okay. So this is an important theorem in this chapter. Okay, so take a few minutes to try to digest it and take a few minutes break. We'll come back at 12:30. Okay. Come back at 12:30.有啲要明白呢個呢個單呢個咁即係話我哋要做4節嘅 line， 咁我就做呢一節嗰時咧，咁我就 PR 1啦。咁因為呢個好細嘅，咁我就即係當佢喐嗰時咧，佢嗰個 value 咧就剔中間嗰節，就代表到成個，就大概代表到成個 line 嗰個位。嗰個 F， 咁所以我就有 F1 PR1啦。咁呢個 F1咧就係咧，我要將呢個 line segment， 即係 exactly 係個 midpoint， 我要 measure 一下個 F 係幾多，咁即係喺呢個方面 measure 個 F， 咁即係話咧，咁所以咧，第一個我哋就喺呢度 take 個 F， 咁所以就係呢個。因為咧，我揀咗個 center 同呢個 y 個果，咁因為佢呢個 width 咧，所以咧佢落咗半 y 就係咁佢 similarly， 咁你明唔明呢個 x 咧？即係呢個，因為我咁咧行嘅，咁個 dr 就係向 x 方面，咁而且我個 dr 就係呢個 length， 呢個 length 就係。所以呢個 x delta x 係嗰個 dr， 咁依家我就考慮第二節啦，即係呢個問題。咁呢個上去嗰陣時咧，咁咧我就又係喺個 midpoint 嗰度揾下個 f， 咁個 f 咧就係喺呢個coordinate咧，呢個 coordinate就係 x 加 delta x 頭號 y， 所以呢度佢都有咁。咁我今次嗰一個 dr 咧係向住 y 大一啲。咁所以就 y hat， 咁個 length 咧 y， 咁所以呢個就係我個 ERP 我同呢啲 vector 我仲有啲 confusion， 呢啲 vector 咧就係我個 F， 即係呢啲 vector field。但係呢個 particle 個 particle 咧，其實咧係咁樣，真係咁樣，即係話嚴格嚟講，你話呢一點個 F 入，呢一點個 F 入，呢一點個 F 入，呢一點個 F 入，但係因為我已經剔到係 DR 咁細啦，冇得再細，咁所以咁細嘅時候，我就總之剔呢一點，就當喺呢一個旅程期間，我感受到，咁所以 所以第三步，我哋今次咧就向緊左邊。咁所以我哋今次咧個 DR 咧就係 minus， 因為向緊左邊嘅方。咁而我哋 take 嘅嗰條係上x 頭 y 加 b y 就係去呢度4個分。咁嘅後邊呢度咧就呢度好冇嘅，呢度真係會有 range of term 嘅，就呢度去到呢度，純粹係會有 range of term 嘅呢個同呢個擺埋呢個擺嚟，除 dx 同 dx， 咁都屈咗兩個，擺出嚟先。Oh, okay. So I should mention again. Last time I mentioned this is that when you do a line integral around closed path, then you have this circle. So that's why I have this, because if I complete the closed path, if I don't complete this closed path, I should have to do it. Are you taking EMF path when you learn about the magnetic field and you do take the line integral around closed path, you'll see this symbol.咩 shape 都唔緊要嘅，係，總之你 close 咗就係要我哋就唔會考慮嗰啲會有框，即係我唔會考慮一個即係中間有框嘅範圍，我哋考慮嘅，我哋考慮嘅嗰啲就只要冇重疊就係，即係好似一條橡筋圈，但係就即係Okay, so let's continue. Okay, so here we have learned Green's theorem, right? So we converted this line integrals in a double integral, right? So in this example, what we are going to consider is the line integral around this closed square loop. Okay, I draw it here. This closed square loop, I have the coordinates for all four corners. Now, this is my field F, right? So if you don't know Green's theorem, you still know how to do it, right? You know how to do it is that you need to integrate over this segment, right? You need to do your parameterization, but by now I think you understand the process already. And then you need to do another parameterization, right? Do the line integral for this one, and then the third one, the fourth one. So now what we are going to do is to make use of what we just learned, right? Instead of actually doing this line integral, following the loop, I'm going to treat this as the double integral, right? For this circulation density here. So that means I'm considering a double integral over this square region. I'm considering this over a square region. Right, so the first, this is the Green's theorem, right? So now the integrand that you have is actually quite simple, right? So the n, right? So this big N is the y component of your field, and this m is your x component of your field, right? So you take the y component of the field, do the partial derivative with respect to x, and then you minus the partial derivative of y for the x component of the field. Okay, so n is xy, m is x squared. Okay, because n is this term, m is this term. So integrating over this region, and this is simple because it's a square region. Remember when we do this double integral for this square region, right? So then I have this constant x limit and this constant y limit, right? So at this point, right? So all you are thinking about is the last chapter, right? So integrating a function of two variables, right? It's a function of two variables over some region, right? So, and actually you'll see that the partial derivative of these two are very simple. At the end, it's just y. Okay, because this partial x squared partial y is just 0. So then you are doing a double integral for this y. Okay, and what you do, right? So again, inner integral first, and then outer integral. So inner integral, still remember that when I'm doing integration over x, then I treat y as a constant, right? And then I have this 2y. So now I do the outer integral, minus 1 to 1. Then I have exactly 0. So that tells you that the line integral around this closed loop is 0. So, and you can verify this, you try to verify this by actually computing, computing the line integral for this 4 sec. So now let me take this example and say, okay, what if I want to consider the line integral around this triangular path? So basically cutting the square into half, I have this lower half triangle. If I want to take this, let me call this C prime. If I want to take the line integral around this C prime path, so what do I need to do? I need to consider this region only. Right, so that means I'm going to have, and let me call this A prime. I'm going to do the double integral only over this triangular region. And the integrand itself, of course, is still the same, right? So, but then you remember that the only thing that we need to worry about is to how to set the limit properly. So this line, of course, is just given by x equals y, right? If I want to do dx first, integrate over dx, then my lower limit here, upper limit over here. So my upper limit is still 1, but the lower limit is y. Okay. And this integrand is the same, so it's just y. So now, what about the outer integral? The outer integral is still go from this -1 here, up to here, right? So it's still -1 to 1. So then this one, if you calculate that, you get this number. Okay. So now you can also ask, okay, what about the upper half of the triangle? Right, so what about the upper half of the triangle? If I want to do the line integral over this part here. So actually, you may know that we don't need to calculate anymore, right? Because I have the result for the entire square, and then I have the result for the lower half of the triangle, right? So the result for the lower half of the triangle plus the result of the upper half of the triangle has to be the same as the result for the entire square, which is 0. Right. So then if I have -2 divided by 3 here, then up here I must have 2 divided by 3, such that the total is 0. Okay. So here is the example here. Now I want you to try to do one on your own. Okay. So the fourth question. Okay. So I have this line integral for this vector field. Okay. And then I'm considering a closed path, but look at the shape. Okay. Just see the questions. Okay, so in this problem, first let me, of course, try to draw the shape of the loop. So I have left half of a circle, right, centered at origin. So left half of a circle, like this. And then radius 5, right? So radius 5. So this is 5, this is -5. And then this loop is formed by this circular arc and also this vertical line over here. So I want to consider the line integral over this semicircle. So the point of this question is to practice how to use a Green's theorem, right? So then my line integral is the double integral over the region enclosed by this semicircular path, right, of the circulation density. So remember, capital M means the X component of my field. Capital N means the Y component of my field. So then first I do partial N partial X minus partial M partial Y. So which is just partial X minus X squared and minus partial Y X squared. Okay. So then that means I have minus 2x minus X squared. Okay. So that means I'm considering the double integral of this function. Okay, you can see that I don't write dA as dx dy because maybe you know what I'm trying to do next is to actually use polar coordinate. Because, okay, when I arrive at this point, right, so I don't need to worry anything about the lines or anything about the path anymore, right? So now I'm purely considering a double integral problem, right, for this function. And because I'm integrating over a semicircular region, then, well, we expect that it would be easiest to use polar coordinate, right? So that's why I write it as double integral in polar coordinate. So what is the R limit, right? So it's a solid circle, right? Although it's just a semicircle, but so it's a solid circle with a radius 5. So that's why I need to go from 0 to 5 for R. So what about theta? So it's not full circle, right? So it's not from 0 to 2 pi. So instead, we start at here, which is pi, right, until here, until this lower line here. So that's what is that? 3 pi divided by 2. Right? Pi divided by 2. 3 pi divided by 2. And then the only thing that you need to worry next is that you need to, of course, convert this function of x, right, in function of r and theta. So minus 2, what is x? X is r cosine theta. R cosine theta. And then minus x squared. So r square cosine square theta. Okay, again, I'm not going to actually do this integral, but it's straightforward enough, right? So okay, so that's it for the last problem. Okay, so I can go back to the lecture notes. Okay, so that's pretty much what I want to say about Green's theorem for now. Right? So you know how to use it, you know how to convert this line integral into this double integral. So now let's go back to the question that I raised, or the comment that I made at the end of the last lecture is that for some of the for some vector fields, when you do this line integral over a closed loop, right, so you get 0 result, and for some of them it gives you non-zero result. And And that ultimately will relate to the properties of the vector field itself. Right. Okay. So, but before addressing that issue, okay, so let's consider the line integral from one point to the other, not closed path now, just from one point to the other. And the question is whether this line integral depends on the shape of the path that we take. Okay, I want to ask this question. So here, again, you can see that I have this simple vector field that I show you in the beginning of this chapter. Okay, so I'm considering my starting point to be P and my endpoint to be R. So now I consider two different paths, the green and the red. The green one is a path that goes directly from P to R in a straight line. And the R, the second choice, is that I go from P vertically up to Q first, and then from Q horizontally to R. Okay. So two choices for the path. And my question is, if I do the line integrals for each path, will the result be the same or not? Okay. So you could imagine that I can take a third path, maybe like this, like a circular arc like this, like a fourth path, maybe something like this. So anything you can think of, you can, in principle, we have infinitely many choices path, right? So, but here I pick these two simple ones. So for the red one, okay, this is exactly the same as what we had in the previous lecture, right? So the previous lecture exactly show you how to do it from P to Q and then from Q to R. So we had the result already. And for the green one, by now, I believe it's also familiar, right? So you just parameterize this straight line, right? This straight path. So that's why I can work with the details. But if you do that, you see that my line integrals over this green path is 0. Okay. On the other hand, for the red path, I'm just taking the result from what we had in the last lecture. Okay, just go back to these slides. You will see that this line integral is non-zero. So just take a moment to think a bit physically. You understand why one is 0, the other is non-zero, right? Because when you are taking the red path, right? So if you look at the arrows around you, the arrows are always, when you're going in the positive y direction, you see that the arrows nearby, so the field nearby also have this positive y component. So that means they are always trying to help you to go up, to go along the y direction. So that's why you get positive work done, right? So, and also when I go from Q to R, going to the left, and you see the vector field around you, nearby you, and you can also see that the vectors are also kind of pointing to the left, right? They all have a negative x component. That's why again, the vector fields is helping you, right? Again, helping you to go from Q to R. Okay, so that's why at the end you get this positive work done. Okay, if you want. Okay. So on the other hand, if you directly go from P to R, okay, so the vector field that you will experience is something like this, right? So let me draw a few more arrows. Something like this. So the vector fields that you experience is either trying to push you to one side or the other. But the direction of this vector field is always perpendicular to the direction of your motion. Right, so that's why you get no work done, right? So F dot this dr dt always 0. Okay, so then of course, now this example is an example where you have the so-called path dependence, right? So the line integral from one point to the other depends on the shape of the path that you pick, right? So this is path dependent. So now I consider another vector field. Again, this is the simple one that I have used earlier in this chapter, right? So the vector field is they're all diverging away from the origin. Just asking the same question. Two paths, whether the vector is the same. This time you'll see that they are the same. Okay. Now physically you can again understand why, right? Because when you go along the green line, right? So in the first half of your journey, right, the vector field is trying to go against you, but now in the second half of the journey, then the vector is trying to push you forward. So at the end, the work done just cancel out. Okay. So similar, when I go from P to Q, in the first half of my journey here, right? So you can see that the vector field is something like this, right? So it's trying to go against you, right? We are trying to go up, right? But then this vector field has this negative, has this down component. So then it gives you some negative work done, but when you go to your second half of the journey, right? So the vector fields start to go up again, right? So then in the second half of your journey, then you have some positive work done, and at the end, the whole thing is zero. But regardless, in this case, I have this 2 points, and then I have 2 different paths, but then the line integrals are the same. However, okay, in principle, this is not enough for me to conclude that the line integral from P to R is path independent, right? Because I only pick 2. If I want to say that the line integral from P to Q, I'm sorry, is from P to R, okay, from P to R is path independence. In principle, really, I have to try all the possibility, right? If I know nothing. So but of course you will understand that that's not the practical way to do it. But in principle, if you want to make that statement, right, one way to prove that is that you need to try infinitely many possibilities. But of course, this is not what we are going to do. I want that then what we need is some mathematical theorem that help us to have a more manageable way, right, to tell me, I give you a vector field and I give you these 2 points, whether I can say that this is path independent or not, okay, without actually doing infinitely many line integrals. So then here comes to the so-called the fundamental theorems of line integrals. Okay, so I will make the statement first, and then I will show you a proof. Okay. So what it says is that consider a region D. So in this case, I mean the entire region in this square, let's say. Okay, or the region D can also extend to infinity, and it depends on what you're considering. But let's say I'm just considering this region here. Okay, the entire region in this square. So the line integral connecting any 2 points. So here I have this point P, I have this point Q, and you are free to pick any other point as your point P, any other point as your point Q. Okay, and I do the line integrals, right? And this line integral will be path independence, okay, if and only if, okay, this function, this vector field function f can be written as the gradient of some scalar function, okay, over this region D. Okay, remember gradient? Okay, so what we learned in chapter 1, In chapter 1, remember that we have a function of two variables. And if we take the so-called gradient, we form a vector field, right? And all the vectors, remember all the gradient vectors are pointing to the direction where, right, the change is the greatest. Right? So now, so you need to remember what gradient is, okay? So now if I have this vector field, right, so that is coming from the gradient of this potential function, then, right, it's guaranteed that you pick any 2 points, you do line integrals, then that will be path independent. Okay, so that is the statement. Okay, and in this case, okay, if this function can be expressed as the gradient of this scalar function, then the f is known as a conservative vector field. Okay, so at this point, we don't worry about what v is, right? So okay, but I'm just telling you that if your field can be expressed as the gradient of some function v, okay, even the v can be unknown at the moment. So, and also, okay, this theorem is not the full statement yet of this theorem yet. Is that not only that is path independent, and also the line integral will be surprisingly easy to calculate. Okay, so this line integral, so at this point, it's meaningless for us to tell you what path I take, right? Because I told you already, path independent. Doesn't matter what path I take already. So that means when I write it this way, that means it's any path I take. Okay, any path that I can take. So then this line integral is equals to the difference of the value of this v function here and here. Okay. So, and this v is known as the potential function. Okay, so when you learn your ENM, okay, you will have the electric field and electric potential. Okay. And your electric field is a conservative field. And your electric field can be expressed as the gradient of an electric potential function. And of course, that one you add a minus sign, okay, but that's the convention. Okay. So this is the statement of this very strong, powerful fundamental theorem of line integrals. So let's try to prove it. Okay, so of course, if you are very cautious, you know that I need to do two ways, right? If part and the only if part. Okay, but here, okay, so I'll just do the if part first. Okay, I'll do the if part. So that means suppose I already know that this field f is coming from the gradient of a function. Right. So then my half integral can be written in this form. Okay. So this f becomes the gradient of some function. Okay. And now I have this drdt dt. So that means I've already done the parameterizations. That means I've already taken some path, right? But I did not explicitly tell you what kind of path I'm taking, but just imagine that it's an arbitrary path that I can parameterize. Okay, so written like this. So now you need to remember the definition of gradient. The definition of gradient, this is something that you again need to go back to chapter 1, where the definition of this gradient is partial v partial x hat plus partial v partial y hat. No question here. That's the definition. Okay, and then dot product with my DRDT. Okay. So now here is the important step. You do the dot product, right? So these terms with this term here, this term and this terms here. So again, we call something you have learned chain rule. Okay. Chain rule. Okay. So if you remember chain rule, you know that this one is simply the total derivative of v with respect to t. So now you can see that if f is not the gradient of a function v, then this one won't be partial v partial x, right? This one won't be partial v partial y, and then you could not apply the chain rule, right? So because it is written as a gradient of this function, then you can apply the chain rule, and that's why you can have this total derivative. And this one, if you integrate it, you realize that it really doesn't matter what path you are taking anymore. It doesn't matter. So, and this one is simply given by the value of your potential function, the value of your v function at the endpoint minus the value of your v function at your starting point. Okay. So now, here I'm go back to talk about the case of the closed loop. Okay, remember I want to say something about for some vector field, if you pick a closed loop do line integral, you get 0 result. For some other, you do get non-zero result. So actually, the path independence of these line integrals will directly tell you something about the result of this closed loop line integral. Right? So the line integral being path independent, right, from P to Q, is equivalent to say that the closed loop line integral is 0. Okay, so let me explain. So the path integral being in the path independent is that I start from P and I end at Q. So when I'm talking about a closed loop, I'm talking about any loop that pass through P and Q. Okay, so I'm picking any loop which pass through P and Q. Can be many different shapes, as long as the loop passes through both P and Q. Okay. So suppose this is the loop I pick. Okay, this is the loop I pick. So then when I do this path integral around this closed loop, I can break it down into two parts. Right. The first part is that I do the path integral from P to Q along this red path A. The second part is that I am taking the line integral from this Q all the way back to P. And remember, the line integral for me to go from here to here, from P to Q along this red path, is the same as the line integral if I go from P to here, because this is the condition I gave you already, path independent. So going from P to Q along this green line is the same as the negative result for the line integral going from Q to P along the same line. When I reverse the direction, whenever I reverse the direction, I just add a minus sign in front. Okay. So that's why we get 0, because this path and this path give me same result. So that's why this path, right, and the negative of this path will give me 0 result. So just write this out explicitly. Okay. So now, what it means is that if I have a conservative field, right? So if I pick any point to start with, and then we take a closed path and go to the original point, then the line integral is 0. So just again, think of electric potential, right? So you have a charge, this electric in the electrostatic field, and then you move the charge far away, and then go back to the original point, right? So the work done by the charge, work done on the charge by the electric field is 0. Okay. So now, this is good, right? So that means as long as I give you a vector field, and then all you need to do is that you are going to inspect whether this vector field can be written as the gradient of some function v. If it can, then you say that, okay, so this is a conservative field. And then I have this nice property for this path independence. But now the some more technical thing is that if I give you a vector field already, okay, first of all, how do I test whether it can be written as the gradient of a function? Right. If it is simple enough, I can guess, right? But if I just give you these two rather complicated function here, so give you a vector field, and then if I want you to test whether it is conservative or it can be written as a gradient of v, then I need a little trick here, right? So suppose, right, so this is the vector field that I give you, again, m n for the x and y component. So if this field can indeed be expressed as the gradient of function v, then that means this field has to be able to written in this form. And that means this capital M has to be partial v partial x. And this capital N has to be partial v partial y. Although at this point, we haven't figured out what v is. But regardless, I have to require that this big M has to be partial v partial x. This big N has to be partial v partial y. Okay. And how do I test that without knowing v? Okay, without knowing v. So then I'm going to use a property that partial v partial x partial y is the same as partial v partial y, and then take the x derivative. I'm going to use this property. So if this capital M indeed is the partial derivative of this function with respect to x, and if this one is indeed this one, so then that means I will have this relation. Okay. So this partial m partial y has to be equals to this partial n partial x. And that means I just need to test whether it is true or not. Okay, if it equation is true, then I know that this vector field is conservative, or it can be written as the gradient of a function v. Okay. So when you look at this, okay, it may again remind you of the circulation density actually, because remember the Green theorem, this circulation density is this one minus this one, right? So saying that this one to be equals to this one is the same as saying that the circulation density to be 0. So now you see that it's all connected. If the circulation density is 0, so what happens if the circulation density is 0? If the circulation density is 0, then you integrate over the region with 0 circulation density, then that means your line integral around that closed path and closing that region is 0. Right. So here, example. Okay, so now again taking this very simple vector field here. This is my M, this is my N, right? So all I need to do is taking this component, do the derivative with respect to Y, and then taking this component, do the derivative with respect to X to see if they are equal to each other. No, they are not. So then I have these two to be not equal. That means this one is a non-conservative, it's not a conservative field, right? And that's exactly agree with the result that we had before, right? So I indeed tried 2 different paths, and I found that the line integral was path dependent. And now the test, I show that it is not a conservative field. So everything is consistent. On the other hand, this example I used, if you again do this test to see whether partial m partial n y is equal to partial n partial x, see that they are equal. And this is indeed a conservative field. And again, for this field, I have done 2 line integrals, right, for two paths, and I saw that the results are the same. Of course, as I said at that time, I told you that that's not sufficient to tell me that this is a conservative field, right? Because I need to consider infinitely many paths. But now we don't need to do that, right? Just do the derivative test. See whether partial m partial y equals partial n partial x is indeed is equal. That means it can be written as the gradient of a function v, and that means this is a conservative field. Okay, so let's stop here for today. Okay, so